So take the first data operand, second data operand, which is of n bits each, apply to the multiplier and product register, and to the product register we have to add the result. Okay, previous accumulated result. Okay. So overflow, underflow. When it comes to the concept of a MAC unit, there is a concept called overflow and underflow. When they are designing a MAC unit, one has to pay attention to the word sizes encountered at the input of the multiplier and the sizes of the add or subtraction unit and the accumulator. As overflow and underflow conditions may encounter, treated as well. So provision of parallel shifters at the inputs to the output of MAC unit, provision of God bits in the accumulator, and provision of saturation logic are frequently used in the techniques to prevent overflow and underflow conditions from occurring in the MAC unit. So now let us consider the previous. Let us consider each of these provisions in detail. Shifters are normally provided at the inputs and output of the MAC unit. See, addition we need to perform continuously. Then we need a shift register which continuously supply the bits. So we need a shifter in the case of MAC unit. Okay. The input register shifter and the input shifters help to normalize the data samples and or filter coefficients. They are fed to the multiplier and to avoid overflow of accumulated result at the output. So likewise, shifters at the output is used to denormalize the result. Okay. So in 2's complementation product, let's say for example in 2's complementation product, or to shift the output by the required number of positions before saving to preserve the maximum possible accuracy. This is done when the number of saved is processed by the several leading zeros. Okay, this is done when this is done when the number to be saved is preceded by the several leading bits, leading zeros or ones. Okay. So next one is your God bits. Sometimes in order to preserve the accuracy, the inputs to the multiplier are normalized. In such case, when the repetitive MAC operations are performed, the accumulated sum grows with each MAC operation. This increases the number of bits required to present the result without loss of accuracy. One way to handle this is the God bits or extension bit. Allow for the growth of the accumulation sum as more and more product terms are added. Just add God bits to accumulate more data. Okay. When the computation of the required sum product is completed, the extension bits may be saved as a separate word. If the required alternatively, sum along with the God bits may be shifted by the required amount of and saved in a single word. Okay. So this is MAC unit with the accumulated God bits. Okay, these are the God bits, and not to avoid the errors because of underflow or overflow. So next we need to deal with the saturation logic. Okay. So with or without God bits, the overflow conditions occurs when the accumulation results become larger and larger. Okay. Likewise, when handling a negative numbers, underflow will occur. The contents of the accumulator become smaller and smaller. So go on decreasing the size, underflow, go on increasing the size, overflow. This is nothing but concept of saturation logic. See, a schematic diagram of saturation logic. There will be a multiplier. We have a least negative value or most positive value, and this is used for sign bit representation, XOR gate. Okay, and it is going to be loaded to accumulator. Accordingly, based on the representation or accumulated product, it can go for underflow or overflow. Okay, and it is all about the saturation logic. One minute. So next one is your arithmetic logic. Again, just try to revise. First we start with the basic architectural features. We started with we completed the multiplier, we completed with the shifter, we sampled with MAC unit. Now we come to arithmetic logic unit. Okay, So in order to shift, multiply and MAC operations, DSP is required to carry out several arithmetic and logical operations. See, to perform all the operations so far we have discussed now, we need an ALU. Okay, that is nothing but completely a concept of ALU. We keep all those things in the ALU. Okay, so there are operations such as addition, subtraction, increment, decrement, negation, AND or not X, compare. They are also we implemented in conventional processor. They are also already there in the conventional microprocessor. It means that ALU of a DSP is similar to ALU of microprocessor with some additional requirements, with some additional features like shift and multiply. A DSP is a general purpose processor in respect of ALU, but with some additional features of shift and multiply. These two are extensions, extensional features of extension with a conventional microprocessor. Okay. And apart from providing arithmetic logic functions, the design of ALU for a DSP, it requires several other features, okay, from the general purpose processor. Okay, along with these requirements, it also requires some other features. Like for example, it needs a status flags. So if you remember, like for example, what we have studied in your BTech 8086 architecture, we have a register called program status word, PSW. Okay, it is used to represent the status of the microprocessor. For example, processor is performing some operations, it will produce the results, then it is going to save the result, indicating the status of the result. So it is being implemented with a concept called status flags. Okay, it is important to know the status of the accumulator after arithmetic logic operations. Okay, let's say for example you perform the addition. What is your result of addition? Let's say you perform some multiplication. What is your result of multiplication? Let's say for example the result of addition is 0. It can be 0 or it can be non-zero. There will be a carry or no carry. So some output status analysis of result. Okay, it is going to be represented with some flags. So let's say for example there is a carry produced, and how you are representing that carry information. Let's say for example you are getting some non-zero output, and how you are going to represent that non-zero output. Let's say for example you are getting some 0 output, and how you are going to represent the status of 0 output. For example your operation resulted in 0 output, and then processor has to understand whether the output is 0 or not. It is being represented by a concept called flags. Okay, so now even our DSP also requires this kind of flags, because you are adding, you are doing multiplication, you are shifting, all operations you are performing. So definitely you need to indicate the status of these operations. Okay, we also need, so that's why we need to take some, or we need to borrow some features from general purpose processor like status flags. Okay, and the next one is the overflow management, and features similar to those explained in the previous section like MAC unit are also required in ALU for the overflow management. And all these are combined with the status. For example, depending on the status of the overflow, for example, you have a flag for overflow, you have a flag for representation of the result is 0, you have a flag for representation of a carry flag. For example, when you perform addition, you got some carry. So to represent that carry, we need to have a carry flag. Okay. And for saturation logic also we need to have some flag. And the next one, architectural requirement, is the register file. A feature that improves the efficiency of ALU is the implementation of large general purpose register. Register file in the sense, as like your conventional microprocessors, where it contains some general purpose register. For example, when it comes to the concept of 8086 like AX, BX, CX, DX registers along with some segment registers, status registers. DSP processor also requires a register file. Register files means a group of general purpose registers. What is the purpose of these general purpose registers? And general purpose register used to store the results, intermediate results. For example, processor is computing some data, processor is working on some data, and it is doing some operation, and it is going to produce some results. Where to store those results? Okay, where to store those results? Generally in processor, general purpose processor architecture, and those results are being saved in the register file, like general purpose register, like for example AX, CX, BX, DX, what we call them in 8086. Okay, and similarly same kind of registers, general purpose registers, we also need in DSP architecture. Okay, DSP processor architecture. This is possibly providing we also need a file of general purpose register in addition to the MAC units in ALU structure or architecture. And after all dealing with all these features, another important requirement or architectural requirement is the bus architecture and the memory. Because processor is to deal with the data. So when it wants to deal with the data, it cannot hold the data continuously. Okay, when it wants to perform the data calculation. So we need a concept of memory. Processor, when it wants to deal with the data, where to store the data, that's why we need a memory. Okay, we need a processor. Again, another important architectural requirement is that we also need a memory. Okay, whatever the data it is required to the processor for computational purpose, that data is to be stored in the memory. So processor, when it is required, it will extract that data, or it can push the data through the address bus and data bus. We already have a sufficient knowledge on what is the concept of address bus, what is the concept of data bus. Okay. Here it is in the diagram. There are two architectures are given. Von Neumann architecture and Harvard architecture. So the two architectures, the baseline is that how you arrange the memory for program requirement and for data storage requirement. Like for example, there are two concepts of data storage: code storage and data storage. If you combine them in a single storage, we call it as a Von Neumann architecture. Code and data both are being stored in the same memory or a single memory. We call it as a Von Neumann architecture. Otherwise, if you have a code storage in a memory dedicatedly, you have a storage for data separately, we call it as a Harvard architecture. And almost all present requirements, architectural requirement is what we follow is the hardware architecture, because we have a dedicated memory for code storage and we have a dedicated memory for data requirement. One program memory, two data memory. Otherwise, you can have additional program memory. We call them as code memory, program memory, data memory, and pro data. You can have multiple memories that you can interface to the processor using address bus or data bus. Okay. On-chip memory. So on-chip memory, it's a concept requires whenever we deal with a specific application where our processor is going to work on specific requirement, not like general purpose requirements. It means every time the task remains same, it will never change in its lifetime. So then we call it as a specific requirement. And for such related requirements, specific requirements, generally or mostly we need a on-chip memory that is sufficient. For example, if you take any example, like for example, if you take a washing machine or if you take air conditioner, and during their lifetime their work remains same. They cannot do any other operations other than related to their work. For such case, we need some on-chip memory. In general, we can have a memory externally that we can interface, but when it comes to the specific requirements like our DSP, we need some on-chip memory. So a compromise between having multiple memories with individual buses for each and having fewer memories and buses is to provide some of the memories along with their buses on chip. Even the processor has to take simultaneous access to all the memories. Only some of these are to be memories external to the DSP, thereby reducing the interconnection of requirements of external chip. So simply the on-chip memory, its main concept is reduce the external connectivity requirements. Okay, so that it takes, say when the processor wants to take some data from external environment, it takes more time. It will spend more time to complete that requirement. But whenever the data resides within the chip, okay, whenever the data resides within the chip, it will go faster. Okay, that is the important advantage of on-chip memory. And another next one, on-chip memory, is the speed. On-chip modules should match with the speed of ALU. Okay, see, ALU works at different speed and on-chip memories with different speed, then there is a problem. So both have to work on with same speed. Okay, but this is not a serious constraint because execution times of complex arithmetic operations such as multiplication are generally longer than memory access time. Okay, so in fast, very often more memory access than one are possible with a single instruction cycle. Next is your size. Size is another major issue of on-chip requirements. If a given area of DSP chip has how many DSP functions as possible must be packed in order to get the best possible performance. You want to accommodate all the functions in a single chip. When it comes to the on-chip, what is the size of chip so that it can be accommodated in the DSP? Okay, that is the important requirement. Data addressing capabilities. Data addressing capabilities means what is the speed at which it can take the data or it can transfer the data. This is nothing but a data addressing capability. For example, whether my DSP processor can at a time handle 16-bit data, at a time it can handle 20-bit data, at a time it can handle 32-bit data. The data processed by the digital signal processing scheme is referred to as data addressing capabilities. Okay, and the very efficient way of data while performing the computation can go a long way in the overall performance of the computation. So you have data residing in the memory. When it comes to the speed of processor, what is its capability to take the data? How many bits at a time it can extract the data, and how much time it can? What is its capacity to handle large data in computational process? Okay. Next, it comes to the another feature which is to be borrowed from the conventional processor design is the addressing modes. So because it is all the programming that we provide for fulfilling our specific signal operations requirement by the DSP. So now how to create a program. Okay, you already have an idea how to create a program, in the sense how to specify the instruction and how to specify the operands. What we call it as a addressing mode. Okay, addressing mode means we need to create a program for our requirement, DSP requirement, processor requirement, operation signal processing requirement. When I want to create a program, how to write the instruction, what is the rule or method, and how to specify the operand. So we know generally in an instruction we have a code, we have a operand. Okay, and how to provide them in the program. This is called addressing mode. So immediate addressing mode, immediately will for immediate addressing mode, in the sense we have a code, immediately you will the operand will be an address. Okay, the operand will be an address. We have also register addressing mode. We have an instruction called add, and the data operand is in register. And direct addressing mode, directly instruction will work on the memory. And indirect addressing mode, for example, you will provide the address of the memory or address of the data in the instruction. So based on the address, the operation will take place. These are all different aspects of programming concept or instruction set point of view when it comes to the concept of DSP processor. The next one is special addressing modes or circular addressing mode. In addition to the addressing modes mentioned earlier, special addressing modes are also provided in the architecture of DSP. Okay, implementation of real-time signal processing to compute DFT or FFT. Real-time signaling processing is enhanced by the provision of circular buffers. Okay, and addressing mode that go with it is FFT implementation requires data to be accessed in a non-sequential way manner. The data for FFT is accessed by what is called bit reversed index, and it is an addressing mode generally provided in the architecture support to FFT operations. Okay, we need to have some special addressing modes for FFT, DFT, similar to process two-dimensional data. It will be advantage to provide a special addressing mode which can help to access the data in organized in a matrix form. So as like we also need a concept called circular addressing mode, like for example shift right register, shift left register. It's concept of circular shifting of data so that our operations will be taken fast, so that it will produce the result faster. The next one is your address generation unit. The function of the address generation unit is to provide the address of the operands required to carry out the DSP operations. Since many instructions execute, the address generation unit should work fast enough to provide the address within the time constraints. So, processor, when it wants to work on some data, it has to generate the address. Okay, because it is all the processor take the data from the memory, or it will keep the data in the memory. In order to perform it, it has to calculate the address of the respective location. So, and how this address generation will be there. So, address generation typically involves, what this address generation typically involves is getting a new value from the immediate operand or register or data. Okay, increasing or decrementing the current address, adding, subtracting to the offset address, and then adding or subtracting to the offset current address, generating a new address from the current address by applying bit reversal operations. Generally, bit reversal operation will be used to generate the address. And then finally, programmability and program execution. Programmable DSP devices need to provide programmability similar to the it should be possible to write programs involving branching, loops, and subroutines. Programmability means how efficiently you are designing the programming. You should have a branching concept, you should have a looping concept, you should have an iteration concept, okay, so that successfully you can organize your instructions, so that processor will execute all these instructions in a fast way. So program control or program counter, generally we call it as they used to store the address of next instruction. Okay, each instruction is broken down into several micro instructions and stored in a micro store as a microcode. Whenever one of the instructions is being executed, corresponding microcode is called from the microstore, in a way very similar to execution of the subroutine in a program. This type of control unit is easy to design and implement using this order. It is nothing but simply a concept of program execution. There will be a microcode for each instruction which is stored in a micro storage. When processor is executing the instruction, the code from the microcode from the micro storage will be fetched and executed. Okay. Generally, concept of program sequencer and speed issues. Harvard architecture we already know. Parallelism, how to improve the speed. Go for a parallel processing. Fetch the instruction, decode the instruction, execute the instruction. Before decoding decoding is happening for the first instruction, try to fetch the another instruction and decode it. And before decoding the second instruction, and before the end of execution of first instruction, decoding of second instruction is taking place. Before end of the decoding of second instruction, fetching of third instruction is going to take place. This is way of a concept called parallel processing or pipeline. This is how you improve the speed of processor. Pipeline. Just now what we discussed about it.